Hey guys, I want to first thank you guys for coming. So the speaker tonight is Dr. Eric Zhao. He is an assistant professor of physics at Florida State University. He's an observational astronomer who has worked in California, Chile, and Denmark before coming to Florida. His research interests include the physics and observational properties of supernova, the explosive ends of some stellar life cycles that can outshine entire galaxies. These supernovae are also used to measure immense distances and determine the origin, evolution, and eventual fate of our universe. So here he comes. Oh, he's coming, I think. Okay, you're good. Oh, sweet, he's got a little laser too. Awesome. All right, so give him a round of applause as he comes up.
Hello. Wow, this is a big crowd. I've never spoken to a big crowd like this before, so. Okay, so I'm going to use my phone as a remote, so I'm not being impolite and checking my messages, okay? So just so that you know. All right, so the topic today is I want to talk to you about discovering our place in the universe, okay? This sounds like a really grand title, but really what we're doing in astronomy is just measuring distances. And just through measuring distances, this simple exercise, we are figuring out today where we are in the universe and, really figuring out our place in the universe. Okay, so this is a really broad topic, and I would just like to give you a broad overview of what we know today. And through trying to explain to you how we measure these distances. So there's going to be a lot of historical facts of how we got here today. And I think that's really important in astronomy, especially. Astronomy is the oldest science around. So what we do today actually depends a lot on what ancient astronomer has done. So astronomers sort of have this privileged position, unique in science, where we are really relying on things that people have found thousands of years ago, and you'll see some of that examples today. Okay, so I just want to begin the talk by giving you a sort of a tour of the universe, and just give you an idea of the scale that we're talking about. Okay, so the universe is really immense, and I just want to show you in numbers what that really means. Okay, so to begin with, the way we measure things is by having a yardstick, right? So me coming from Canada, my yardstick is in meters, and my son is just about 1 meter, and we'll use him as a yardstick to begin with, okay? And you'll see that I'll have the numbers here in meters and in how fast it takes for the light to travel that same distance, okay? So right now, for light to travel from one end of my sun to the other, it takes 0.0001 light second, right? So this is a very, very small number. But you'll see that this measurement in distance using light is actually going to be very useful for us when we're going to talk about very, very large distances. Okay, so we start from the size of the Earth. The size of the Earth is about 10,000 kilometers in width, right? And it takes light about 0.01 second to travel across. This is the reason why, for most of the human history, we do not know that light has a limited, finite speed. It's not until recently that we know that, because in our daily life, we don't see light as a finite speed, right? We turn on the flashlight, it goes immediately. But this is a fact of nature. All right, so here I have this very large orange object. Anybody know what this thing is? This orange thing? That's the sun, yes. Very good. So You can see that there's some sort of flare going on there. This is what we call prominence. And I want to show you this just to tell you about the distance to the sun, right? So the distance to the sun is in a large number in meters now. So I'm not going to spell that out. Now is convenient to switch to the time unit, right? So now it takes about minutes to get to the sun. So if the sun were to disappear on us right now, it will take us a few minutes to notice. Okay? And also I want to show you the size of the sun, right? This just by putting the Earth next to it. All right, so there's the Earth there. And you can see that the Earth can fit through one of those prominences, right? These big loop going out. That's bigger than the size of the Earth. That's how big the sun is compared to the Earth. Now, the sun is not the biggest object in the universe, right? It's not the biggest star. One of our neighbors called Betelgeuse. This is one of the largest stars that we know, okay? So this is an actual picture of Betelgeuse. This is one of the very few stars we could actually resolve since it's so big, okay? So this pattern on this star is real. I actually have drawn the sun on this same plot there as well. Can you see the sun there? Just by comparison in the size. Okay, if you can't see, I can help you out there. It's that little dot there. Okay, so this is Betelgeuse compared to the sun. Remember how big the sun was? All right, this is Betelgeuse compared to the sun. Maybe you can't see it very well. I'll zoom in a little bit more. There's the sun. Okay, so it's very, very tiny compared to Betelgeuse. All right, so now let's take a journey out toward the edge of the solar system, right? So going out to when we talk about the size of the solar system, that is measured in light hours. So it takes light hours to get out of the solar system, right? Compared to minutes getting to the sun. Okay, now we have escaped the solar system. How do we get to the nearest neighboring solar system? That's Alpha Centauri, and that takes years, right? So going to neighboring stars, now we're going to take years for light to travel from our solar system to even the closest stars. Okay, and there's been a very recent, very exciting discovery that our nearest neighbor actually harbors planets. So this is Alpha Centauri, but Proxima Centauri, which is actually a star in this stellar system that is closer to us, actually has planets and possibly Earth-like planets in the solar system. So it is possible for us to explore that, hopefully in the near future. All right, so let's now head to the center of our galaxy, right? How long does that take? Now that takes thousands of years, okay? So for me to get to the center of my own galaxy, it takes, at the speed of light, it takes thousands of years for me to do. That's the size of the galaxy. Next stop, let's go to a neighboring galaxy, so getting out of the Milky Way and going to another galaxy. And now that's going to take you millions of years, even if you can travel at the speed of light, right? So that's immense. And there's a little supernova there that we'll see again later in the talk. Okay, so this doesn't show up very well. Does anyone recognize what this picture is? This is a very famous picture taken by Hubble. No, and so this is the Hubble deep field. So this is a very famous picture. So what the astronomers have done is they picked a blank part of the sky where they thought there was nothing there, and they just stared at it with the most advanced telescope we had at the time, which is Hubble Space Telescope, and just stare at that blank part of the sky, collecting light from distant objects. And this is what they saw. is full of galaxies, even in the most empty part of the sky. So this is really going toward the edges of the observable universe that we could see. And still there, we got lots of galaxies there, okay? And to get to this, these galaxies, it'll take you hundreds of billions of years, even if you could travel at the speed of light, okay? And that's about the size of the universe, is hundreds of billions of light years across. And if you zoom in on one of those and you see a spiral galaxy like that, and it's very familiar to us because that's what Milky Way looks like. So you wonder who's living across the other side of the universe. Okay, so now let's get to the meat of the talk. Well, how do we go about measuring these really vast distances, right? How do I know these things are really that far away? Okay. So this goes to how astronomers measure distances through this scheme of distance ladder. Okay, so we figure out how to measure the closest things, and we figure out other techniques to measure things that are even further out. And if there are overlaps for a certain object, maybe for a galaxy, that we could use both methods, then we could use the ladder. We could use that as a ladder to climb up to the next step. Okay. So this is what we do. We use, so I'll be talking about these 4 methods in this talk. Okay, so let's start from using sticks, okay? So that's the easiest way to measure distances, right? Use sticks. So I wanted to point out here that, remember Christopher Columbus discovered America in 1492. But at that time, he had grossly mistaken the size of the Earth, that he thought he had arrived in Asia. Okay, this is 1492. So from that information, can anyone guess when did we as a species know how big the Earth actually is? When do we finally figure it out? Take a guess. I like the talk to be more interactive, so feel free to yell it out, and if you have any questions, also feel free to interrupt me.
1950.
1950? Any other guesses?
1951.
1951. And you're all very wrong, okay? The answer is 200 BC, okay? The ancient Greek astronomers have already figured out quite precisely the size of the Earth at 200 BC. This is 1700 years before Columbus, okay? And Columbus actually knew about this number. He just chose not to believe it, okay? So Eratosthenes is the guy that measured the circumference of the Earth using only 2 sticks, okay? So I got a picture here of how he actually did it. So this is like a map of the Earth. And you imagine 2 sticks at 2 different places on Earth, okay? So at that time, the ancient Greek astronomers had no doubt that the Earth is round, okay? They don't even think about that as flat. And this is the reason why, okay? When you look at 2 sticks at the same time, they don't measure the same shadow. They don't measure the same shadow length. And that is telling you the curvature of the Earth, right? So if you have a completely flat Earth, then you'll get something like this, where your shadows will be the same size. But if you're getting a little bit of curvature, then you're going to have different shadow lengths, maybe very short on one side, and then some length on the other one, okay? So this is how Eratosthenes used the sticks to measure the size of the Earth, because you can imagine if the Earth is more curved, meaning it's smaller, that you'll get a bigger shadow, right? And if it's less curved, then you get a smaller shadow. So he's measuring the size of the shadow and using geometry to figure out what the size of the Earth is. Okay? And does anyone recognize where I steal these pictures from? Does anyone recognize this picture? So this is Carl Sagan's Cosmos. This is one of the best TV shows ever made. So you guys should check it out, okay? So, you know, Cosmos has been remade recently, but the original series made by Carl Sagan is still very, very good and very relevant. Okay, so that's measuring the size of the Earth. But what happens when we need to measure things that are even further away? Okay, so ancient astronomers has figured out this method called parallax, and this is very important in astronomy. Okay, all right. So this is an experiment that we can all do, figuring out how to use parallax to measure distances. Okay, so what you could do is stick your finger or a pen in front of your face and close one eye, and then try the other eye. You have to do it. You can't just yeah, try it. Close one eye and then close the other, and look at the place of the pen compared to the background objects. Okay? It looks silly. Don't make me look silly by myself. Let's all try it. Okay? All right? Do you see it move? Yeah? You see it move, right? Now pull it further away and try and look at it again. Did it move more or less? Move less, right? So by looking at how much an object has moved from the two different perspectives, then you can figure out how far away it is. Okay? So what I have just described to you is depth perception. All right? This is why we have two eyes with some separation. This is how I could tell how far things are away from me. Okay, so you could try and walk home today with one eye open. Don't drive with one eye open, but try and walk with one eye open. Maybe you'll trip and fall down, and you'll understand how important it is to have two eyes that with a certain separation. Okay, so astronomers use the same principle, right? So if say the Earth is orbiting around the sun, which isn't a given at the moment, right? Right now we're in ancient Greek time, 200 BC or so, right? We don't know the Earth is going around the sun, but let's say if the Earth is going around the sun, we can use the entire Earth's orbit. Let's say we observe a star in the summertime, and we observe it again in the wintertime, and see how far it's moved across the background, more distant object, but more distant stars. Then we could figure out the distance to that star. Okay. Now, when we talk about parallax, I got to bring in this topic of who removed the Earth from the center of the universe. Remember, I think most of us are familiar with this story. The ancient Greeks actually got it wrong. They had claimed that the Earth is at the center of the universe, it's not moving. Okay, that's called the geocentric model. And it's not until 1500s where this man here, can anybody name this guy? Copernicus. Yeah, Copernicus has removed us from the center of the universe. Okay. But the Greeks have kind of been getting a bad reputation for this geocentric model. But I would just like to do them justice here and explain to you why they believe that. There's a very good reason for them to believe in the geocentric model. Okay. Yeah, right. So, right. So, does anyone want to guess as to why the Greeks believe that? Believe that we are at the center of the universe?
They saw the sun moving and not us.
They saw the sun moving, exactly right. This one reason, right? We don't feel it. We feel like we're stationary, and it's insult to our senses if we are moving, right? It's not natural for us to feel like to say that we're moving. But there's another very important reason, and this is actually the one that stuck. And the answer is on the slide. The answer is parallax. They observe all the stars in the sky, and they observe no parallax. They were never able to measure any sizable parallax from any stars. Okay? And that's how they concluded that we're at the center of the universe and we're not moving. Everything else is orbiting around us. Okay? So they have a very good reason for believing in that. And this is the example that I gave. Everybody's familiar with the Big Dipper, right? In the summertime, it looks like this at a certain time. And if you go to the wintertime, at the same time, it might look like that. The pattern's the same, right? If there's a star that's close to us and parallax is at work, then this pattern is going to be screwed up, right? The pattern is going to change. But the pattern never changes. And in fact, for all the constellations that we know, the patterns don't change. And that's why the Greeks believe in the geocentric model. Now, there are rebels among the Greek astronomers. There's this crazy guy here called Aristarchus. Okay? So he believed that the Earth is orbiting around the sun. And the reason why we don't see any parallax is because they're so far away. And in fact, he believes that all the stars in the sky are suns. And they don't look as bright because they're so far away. Okay? What a crazy guy, right? But he turns out to be right. So I just want to point out that not everybody believes in the geocentric model then. All right. So we talked about Copernicus removing the Earth from the center of the universe. But is the sun at the center of the universe? This is the part that the textbook doesn't really teach you. Is there an answer? Did I hear it? What? Heliocentric. Yeah, right. So we know that we're orbiting around the sun, but is the sun at the center of the universe? No. All right, that's actually very good. You gave it away. All right, so no, it's okay. I like it. So this is the night sky when we look toward the Milky Way. Okay, so you look at this. We live in this galaxy, but when you look at this picture, can you tell where we are in the galaxy? We're sort of on the edge, right? We're living in the disk, but it's very hard to tell where we are in the disk. Okay, so that's an observational problem. Okay, so before we get into this, I want to introduce this type of stars called Cepheids. This is very, very, very important in the advancement of astronomy. This is actually a breakthrough. So Cepheids is a very strange name. It's just named after the first star that shows this variability. So Cepheids are variable stars. They change in brightness. Okay, and when I talk about this discovery of Cepheids, I always like to emphasize the contribution of these women working at Harvard Observatory at the time. And this is one of the exam questions that I always put on to make sure the student actually were listening in class and not falling asleep. So it says, how many of the following statements are true about the Harvard computers in operation at the Harvard Observatory in the early 1800s? Okay? So let's all try and do this. They are the first mechanical devices used to process astronomical data. That's false, because these are, when we talk about these Harvard computers, I'm actually referring to these women. Okay, these group of women. They were cheaper than hiring men. That's absolutely true. So the guy who hired the director of the observatory at the time, he didn't hire these women because he wants equality. He actually hired these women because they're cheap. Okay. They led the creation of the modern spectral classification scheme. That's absolutely true, and that's very important. They contributed to the discovery of white dwarfs, and that's true. And right, I want to show you these women here. So this picture here is basically the all-star team in astronomy. Okay, these women have made so many discoveries. It's just amazing how much talent is there in this one room. One in particular is what we should focus on today is Henrietta Swan. Okay, she discovered this relationship for these Cepheid variables that correlates the brightness of these variables to their period. Okay, so that means if I observe a Cepheid star from somewhere far away, all I need to do is figure out its period and how fast it varies. Okay, so I just have to take pictures of that star night after night and watch, and then measure the brightness of that star going down and up and down and up. And if I could figure out the period of that variation, then I know how bright it actually is. So then I measure how bright it appears to be. Then that gives me the distance, right? If I know how bright something actually is and how bright something appears to be, those two numbers gives me the distance. Okay, so that's the concept. So she actually didn't know how these stars work. She just knows that from the period we could tell the distance from these objects. And that's a huge breakthrough. All right, so going back to this, I needed to talk about Cepheids because this is going to be important now. All right, so going back to where is the sun in our galaxy? Now, so enter this player called William Herschel. So William Herschel is you can consider him the first modern astronomer. He's the first guy who actually used the telescope to measure things, okay? And he was intrigued by this question, and he wanted to figure out where the sun is in the Milky Way. So he made this map. What he did was very simple. He counted the number of stars in every direction of the Milky Way disk, okay? So this is what he concluded. He concluded that the Milky Way is a disk. Okay, no surprise there. And he also concluded that the sun is roughly at the center. Okay? And this view has stuck in the astronomical community for a long, long time, for decades. Okay? So what Herschel has also done, that's important in astronomy, he's made a catalog of all these fuzzy objects in the sky. Okay? So this is for cheating. I just put up the objects from the Messier catalog, but Herschel's catalog is much bigger, much more comprehensive. But in terms of the type of objects that is included in the catalog, it's very, very similar. And there are two types of objects in particular that are composed of mainly. So the catalog is composed mainly of these two types of objects here. Okay, one of them is called globular cluster. So it's this very spherical-looking cloud of something. Okay, globular cluster. And another thing, that's these spirally things that back then they called spiral nebula. Okay, so you have to remember at this time, people didn't know what these things are. They didn't know these are galaxies. They didn't know these are stars, okay? So these are just fuzzy objects, and in the telescope, they look almost the same, except for some shape differences, right? Okay, so then came a pivotal moment in astronomy history called the Great Debate in 1920. Okay, so there are these two guys, Curtis and Shapley, had this great debate. Okay, so when I studied this in astronomy when I was in school, I always picture these two men like shouting at each other, fighting with each other, sort of like a Jerry Springer style on stage. But I learned recently that it was very boring. It was just one guy gave a talk and the other guy gave another boring talk. And then they just sort of hash it out afterwards. But it turns out that it's one of the most important event in the history of astronomy. Okay, so what these men were debating about were a lot on the nature of these fuzzy objects that we're looking at. Okay. The first thing, they also want to figure out where the sun is in the Milky Way. And Shapley, being the young and rising star, he wants to go against the establishment. So he was trying to figure out new things to try and overturn the old ideas, right? And Curtis is the old guy. So Shapley came up with this new idea. So he said, instead of counting stars in the sky, in the Milky Way, how about we count the number of globular clusters? He didn't have a very good reason for doing that, but it turns out to be the right thing to do. So when he counted and measured the distribution of the globular cluster around us, he was able to show that the sun wasn't in the center of the Milky Way, it was right at the edge. Okay? So Shapley is actually one of these important figures, just as important as Copernicus. Copernicus removed the Earth from the center of the universe, and Shapley has removed the sun from the center of the universe. So basically, these two men have put us down and tell us that we're really nothing special. We're just really a citizen of this vast universe. Okay? Now, they also debated on this object, these spiral nebulae. Now we know these are galaxies, right? So Shapley, on a hunch, he did not believe that these spiral nebulae are outside of our galaxy. He believes that these things are like globular cluster; they are part of our galaxy, because otherwise the universe would be way too big. He just, he couldn't imagine that. But Curtis is on the view that he's supporting this view called island universes. He's calling these nebular galaxies actually galaxies like the Milky Way. And there are island universes all around the universe. So Curtis turned out to be right in this respect. Okay. So the tiebreaker came with this guy. Okay. So does anyone recognize this man? His name is already mentioned once this evening. Very quiet. Hubble, yeah, that's right, Edwin Hubble. So he's the tiebreaker in here. So he actually measured the distance to our closest neighboring galaxy, which is Andromeda Galaxy. So how did he measure the distance to the galaxy? Cepheids again. So, hello? There we go. So he uses Cepheids again to figure out the distance to Andromeda Galaxy. And the result was astonishing. It was 100 times the size of the Milky Way. So it has to be outside of the Milky Way. Okay? So this is only one contribution from Hubble. You'll see later on he has he's not done. He's not quite done yet. Okay? So I never skip a chance to show pretty pictures in astronomy. Okay, so this is the Andromeda Galaxy, and Hubble was able to find a Cepheid in that galaxy and measure the period. Then he was able to find the distance to this galaxy. And there are other spiral galaxies like these, very pretty, beautiful spiral arms, right? Like this one. Sometimes with bars in the center. And some of them like this. And there's a purpose for me to show this to you, okay? So I want to ask you, why did Herschel get it so wrong? How did he figure that we're at the center of the... Why is it when he counts stars, he got the wrong answer? So the answer is in this picture here. How did he get it so wrong? Yeah? There's only one galaxy? There's more than one galaxy? But remember, he's counting stars in every direction, right? So he's counting the same number of stars going toward the center and the same number of stars going away from the center of the galaxy. So what went wrong there? No, yell it out. No. It's the answer is in the picture. What's going on in this galaxy? There's a very prominent feature in this galaxy. That's the answer. Huh?
It's rotating.
It's huh? So what's causing all this darkness on one side? This is called the black eye galaxy. Like someone punched it in the face. What's causing all this darkness there? Huh? Not as exotic as that. It's actually dust, okay? It's actually dust. And dust is the reason why Herschel got it so wrong. Because when we look toward the center of the galaxy, there's more dust there. So that's why you count the same number toward the center and away from the center. That's the answer. Okay, so dust sounds boring, but dust is actually where we came from. Just a side note. Okay, so now moving on to the next stage, and I had to bring in this guy, right, Einstein, and his general theory. Okay, so I'll try to simplify things as much as I can. So general theory is a beautiful theory, right? The math is very complex, but the result is something that's very simple and elegant. And this equation here, okay? So if you ever want to tattoo anything on your body, this is it. This is not likely going to change, okay? So forget your boyfriend's or girlfriend's name. Tattoo this one. So what it's actually saying is very simple, and it's mind-blowing, okay? So what it's actually saying is the geometry of the universe depends on what's in the universe, okay? So it's saying that whatever's in the universe can change the geometry of the universe, okay? So right now, me being a piece of mass standing here, I am curving the space around me right now, okay? So that's how you could think of general theory, is describing the relationship between things and the space around us, okay? So this is going to come back later in the talk. So I just want you to know what general relativity is trying to say. Now, Einstein has famously added this term in there, a lambda term. So this is basically a constant in there. If you take a derivative of this, the constant goes away. So he's actually allowed to do this. It doesn't change the equation. But the motivation for him to add this is wrong, okay? So Einstein's motivation for adding this is he's learned the lesson from Copernicus and from Shapley that we're not special at all, right? We don't occupy a special place in the universe. Now, he also figured that we don't occupy a special time in the universe, all right? So this is the reason why he believes in a static universe. So in order for us to be not special in time has to be always the same. The universe has to be always the same and not do much, right? So this time is the same as any other old time, okay? So this is Einstein's sort of hunch. He figured that it will be strange if the space is actually moving, expanding or contracting. So he put in this term to keep a static universe. If he doesn't have this term in there, the universe is naturally expanding or contracting. Okay, so we'll go back to that. Now, Edwin Hubble, by 1929, he has measured distances to several galaxies. Okay, using Cepheus again. Remember, Cepheus, very important. And then he also collected velocities from his fellow astronomers. And then he made this very, very beautiful and very, very important plot. Okay, so on one axis is distance, on the other is velocity, how fast things are moving away or toward us. And he made this astonishing find that almost everything is moving away from us, okay? And the further away something is, the faster it's moving away from us. Now, if you go back and read his original paper, he was very careful about how to interpret this. But this is clear evidence that the universe is expanding, space is expanding. So everything is moving apart. If you draw the picture, if you picture like a galaxy being stuck on a balloon and you blow out the balloon, then you'll see that things are always moving away from you. And the further stuff is moving away from you faster. Okay, this is a natural consequence of expanding universe. So Hubble has proved Einstein wrong. Okay, so the universe is expanding, very important. So Einstein actually visited Mount Wilson and visited Edwin Hubble afterwards. And Einstein has reportedly remarked that the inclusion of this cosmological constant, remember, to keep the universe constant, that was the biggest blunder of his life. Okay, he thought, oh, what a stupid thing I did. You know, Edwin Hubble actually showed that the universe is expanding. Okay, so I want to introduce the last distance indicator. So this is the stuff that I'm working on, supernova, type 1a supernova. Okay, so type 1a supernova works very much similar to how Cepheids work. So Cepheids are variable stars. Their brightness go up and down, up and down, up and down. Okay, supernova goes boom. So the brightness goes up and then it goes down, and that's it. Okay, you have one shot to measure it. That's the difference. But the way we use it is very much similar. Okay, so this guy, Mark Phillips, is my old boss in Chile. He had found this relationship that the brighter supernova tend to get faint slower. Okay, so you can see that these bright guys are going slower, and these faint guys are going faster. So all you have to do is measure supernova on this tail and measure how fast it declines. Then you know its actual brightness. When you know its actual brightness and you know how it appears, then you know the distance. Okay, it's very similar to how Cepheid works. So I put them in the same category as Henrietta Swan. Okay, so with that method, we were able to make really beautiful Hubble diagrams. Okay, so remember the Hubble diagram that Hubble had made originally, right? This kind of scatter plot. We're able to do much better now. So this is a very recent Hubble diagram that we did in 2012. Okay, so this is a type 1a supernova. Can everybody find the supernova in this picture? So supernova is important, and this picture is showing that. This is a supernova. What is a supernova? Supernova is a stellar explosion. This is how some stars die. Okay? So imagine that this is a whole galaxy. This whole galaxy contains hundreds of billions of stars. And one of them went kaboom. And that's what it looks like. So it's almost as bright as the whole galaxy. So that's why type 1a supernova is very important, because they're really, really bright. And you can measure them from very, very far distances. Okay, that's key. Okay, so here's another game for you. I think this is good enough for you to see where the supernova is. So this is the before picture and this is after. Right, there's a supernova there. There we go. And when you go out to further and further away and trying to find supernova that's really distant, and this is what it would look like. So we see a little dot beside a galaxy like that. So this is what astronomers do. We try to find these supernova from nearby and from far away to make these Hubble diagram. So what we're trying to do here is trying to map out the expansion history of the universe. So basically the history of our geometry. Okay? So this is so we have gone from the original Hubble diagram here in the 1920s to this diagram in the 1970s. So you can see that this little square contains what Hubble had originally done. Okay, so this guy Sandage had collected bright galaxies to do this diagram. Now that method it pales in comparison to Type 1a supernova. So Type 1a can go out way further than what bright galaxies or what Hubble can do. Okay, so this is how we're able to measure the geometry all the way from halfway across the universe. Okay, so I want to show you that result. So in the 1990s, there's two independent teams of astronomers. So led by these two guys here. They look kind of silly there. They are trying to find supernova to measure this number called the deceleration parameter. Okay, so you imagine the Big Bang happened, right? So everything is expanding. Hubble found that everything is expanding because of the Big Bang at the very beginning. Now we know the universe contains matter, right? Because you and I are standing right here. So there's mass in the universe. So because there's mass, we expect the universe to eventually contract under gravity. So if I have gravity, you have gravity, we will eventually pull toward each other and pull the space back toward each other. So astronomers before the 90s, they were sort of expecting to find this number called deceleration parameter. So they're fully expecting the universe to come back on itself again because of gravity. Okay? But to their surprise, the supernova data is telling them the expansion of the universe is not slowing down, it's speeding up. Okay? That's messed up. And to be honest with you, we have no idea what's going on. Okay, so this is one of the biggest mystery that we have in physics and astronomy today. Okay, and that got these silly folks a Nobel Prize in 2011. Okay, so this is what you hear in the media called dark energy. Okay, this is a very catchy name, like dark energy, like we actually know what we're talking about. But we don't. We have no idea what we're talking about, and that's why we call it dark energy. We don't have any idea what this is. The only thing we could tell that it is a property of space itself. It seems like the more space that is being created, the bigger the effect of dark energy. Okay. Right. So this is a picture from the same supernova data that you can actually see a past deceleration happening. Okay, so that deceleration that the astronomers are trying to measure, it's happened before. It's happened halfway across the universe. But right now, today, the expansion rate is speeding up again, taken over by this mysterious dark energy. Okay, so if you remember general relativity, right? The geometry of the universe is equal to the stuff in the universe, right? So what we have done with supernova is measure the history of that geometry. Now we can infer what's in the universe. All right, so this is messed up. This is what we have for our universe today. Okay, so 73% is called dark energy. 27% is this thing called dark matter. That's another story that I haven't gotten into yet. So that leaves about 4% of matter, like the table, the stars, the galaxies, light, everything that we know contributes 4%. We have 96% that we don't know, okay? So we actually know very precisely how much we don't know. Okay, so these are the known unknowns, right? If you remember Donald Rumsfeld, he actually was right. This is the known unknowns. So the biggest blunder, like going back to Einstein again, this lambda term, remember he added in there to stop the universe from expanding. But that turns out to be the best fit for the current cosmology. And this lambda term, if you change the number, if you change the physical number, it actually can be dialed up to create this acceleration. So it's allowed in general relativity. So even Einstein's biggest blunder is still holds true today. So this guy is quite amazing. All right. So Einstein coined this phrase, does God play dice? This is referring to this incompatibility between the two most successful theory that we have to describe nature. One is general relativity, right? Is wildly successful at describing the large things. And also quantum mechanics, that is very successful at describing the little things, little particles. But these two theories are fundamentally incompatible because the uncertainty principle in quantum mechanics doesn't sit well with Einstein, right? Einstein doesn't believe that. This is why he said the term, God does not play dice. So here I just made a note here. If we naively think dark energy is some sort of vacuum energy from quantum mechanics, the discrepancy between the observation and the theory is something like 10 to the 100 times off. Okay, so this is the worst prediction in physics. So that means we really don't understand what's going on. But it's also pointing the direction of where to find the problem. Okay, so dark energy to me is this crucial thing that we can solve by looking at it deeper, right? And by looking at it deeper, we're really solving that the question of the incompatibility between these two fundamental theories. So to me, the ultimate goal of physics is to find the theory of everything. And I believe we're close, right? We got two that's really successful. So I really think this is the right direction to look, even though we don't understand it very much. Okay, so that's sort of the summary of my talk. So what have we learned from 2,000 years of distance measurements? We've learned that we really don't occupy any special place in the universe. And also, the universe is mostly made of stuff that we don't understand. Okay? And that's the current state right now. I hope you enjoy that. Okay, thank you.